In order to find zeros of quadratic functions, we'll begin by looking at the x-intercepts for two different quadratic functions. If we first consider f of x equals x squared minus 9, the graph of which is provided here below, we see that we have two x-intercepts, one occurring at the point 3, 0, and one occurring at the point negative 3, 0. If we consider the second function graph below, which is g of x is equal to x squared plus 9, we can clearly see that g of x has no x-intercepts. So we have that important graphical difference between these two functions. All x-intercepts for a function can be referred to as zeros of that function, because for that x-coordinate, in the case above either positive 3 or negative 3, for whatever that x-coordinate is, let's say c, f of c is equal to 0, meaning if we evaluate the function at that x-coordinate, the resulting y-coordinate is 0. Clearly then, f of x has two zeros, since we have two different points where our y-coordinate is 0. But g of x obviously has no x-intercepts, and therefore doesn't have any obvious zeros. However, every quadratic function does have exactly two zeros, and we'll investigate how that can be, considering that g of x has no x-intercepts. In example 1, we're given that function f of x again. In order to find its zeros, what we can do is take that function and set it equal to 0, which in this case would factor as x minus 3, x plus 3 is equal to 0, giving us two solutions, x equals 3 and negative 3. This is essentially the same information we found graphically above, but we can also identify those results algebraically. And we can apply the same approach to trying to find the zeros for what should be g of x, which is x squared plus 9. So we'll start off with the same idea. We'll take x squared plus 9 and set that equal to 0, since what we want to find is where our function would be equal to 0. Since we can't factor this expression, what we can do is apply the quadratic formula if we insert a placeholder term, 0x, and then we can solve this by evaluating that quadratic formula, which is the opposite of b, plus or minus the square root of b squared, minus 4ac, all over 2a. Since our value for b above is 0, we would get 0 plus or minus the square root of 0 minus 4 times 1 times 9, all over 2 times 1, which would give us plus or minus the square root of negative 36, all over 2. If we're only considering real solutions to our function g of x is equal to 0, then at this point we would have no solution since we have the square root of a negative value. However, if we start to consider complex solutions, meaning we let I equal the square root of negative 1, we open this up to have two solutions. That would mean we could rewrite this as plus or minus I times the square root of 36 divided by 2, or plus or minus 6i over 2, which would be equal to plus or minus 3i. Again, we have no real solutions in this case, since we're taking the square root of a negative value, which is why our function has no x-intercepts. But we do end up with two complex solutions, meaning this function g of x does have two zeros, which in this case are complex numbers, 3i and minus 3i. This means we can go back and add some addendums to previous statements we made. So every quadratic function will have exactly 2 zeros. Which may be complex zeros. We'll end up with complex zeros if we have a case where our function has no x-intercept. And what we can see by plugging in the values that we found below, if we were to plug x equals 3i into our function x squared plus 9, we would get that quantity 3i squared, where keep in mind that I squared is equal to -1. So this would give us -9 plus 9 is equal to 0. And g of -3i is going to be equal to -3i, that quantity squared, plus 9. Here, -3 squared will be 9, and I squared will again be -1. So we'll get -9 plus 9 is equal to 0. This means we have two values, 3i and -3i. They give us function values of 0 whenever they're substituted in. So while g of x has no x-intercepts, g of x does have zeros. At x equals 3i and -3i. Just like our function f of x had zeros at -3 and +3, the only difference here being in one case we have real solutions, and in the other case we have complex solutions.